In this targeted learning brief, we'll discuss how the ratio of bias to standard error affects confidence interval coverage. Statisticians analyze data in order to learn something about the world. For example, we might want to know whether a new drug decreases mortality, so we analyze data to estimate a parameter of interest, such as a risk difference. We also quantify the uncertainty around the estimated value. To construct a wall-type confidence interval, we add and subtract approximately 2 times the standard error from the estimate. This approach is valid most of the time, as long as the estimates are normally distributed. When we repeat the experiment over and over, we obtain different parameter estimates and different bounds on the confidence intervals. Both the estimate and the intervals are random. The width of the confidence interval depends only on the estimated standard error, not the value it's centered on. As sample size increases, confidence intervals grow narrower and narrower. In this era of big data, confidence intervals can be quite small. Although that sounds like a good thing, we'll see that if you have a biased estimator with a small standard error, you can easily be misled into drawing the wrong conclusion. In the example shown here, the confidence interval includes the true value of the parameter, psi0. When we repeat this experiment many times, we obtain many point estimates. The normal curve centered at psi0 shows their distribution. We can also see their associated 95% confidence intervals. Confidence interval coverage is the proportion of confidence intervals that contain the truth. We expect that 95% of the time, the true value will lie within the bounds of the confidence intervals we constructed. 95% of the confidence intervals will cross the dotted red line. But what happens when our estimator is biased? We know that the point estimates will not converge to psi0. Now let's see how confidence interval coverage is affected. The black curve shown here describes an estimator that is no longer centered on psi0. Point estimates and confidence intervals have been shifted right by positive bias equal to 1/2 of the standard error. The nominal 95% confidence intervals were constructed correctly, but because they're shifted, coverage falls to only 92.1%. Watch to see how coverage changes as bias grows from 0 to 4 times larger than the standard error. We can calculate coverage using the formula shown here, where phi is the CDF of the standard normal. Again, when the estimator is not quite normally distributed or the estimated SE is imprecise, this is an approximation. But clearly, when bias swamps the standard error, coverage is quite poor. Is this likely to happen in practice? And could it change the substantive conclusion drawn from the statistical analysis? Unfortunately, the answer to both these questions is yes. When we analyze large data sets, we get tight confidence intervals around our point estimates. If we use traditional parametric models in high-dimensional settings, those point estimates are almost certainly biased. Remember, standard errors decrease as a function of sample size, but bias doesn't. When an estimator is asymptotically biased, or more generally, its bias to standard error ratio converges to infinity, then, even when it is normally distributed, coverage goes to 0. Even in practical settings with thousands of observations, we might be in this situation, and when that happens, the only thing we know about our nominal 95% confidence interval is that it almost certainly excludes the truth. For many statistical estimands, asymptotically unbiased estimation requires data-adaptive machine learning. There are many good machine learning algorithms out there that can reduce model misspecification bias. Superlearning is a meta approach that lets us harness the strengths of all of them, but even then, models must be optimized towards a plug-and fit of the statistical estimand. A subsequent targeted maximum likelihood estimation update step applied to the superlearning fit provides the bridge from machine learning to formal statistical inference and reliable hypothesis testing and confidence interval coverage. Superlearning and TMLE are introduced in other targeted learning briefs. You can also watch the Targeted Learning webinar series on YouTube.